Salam and welcome everyone. So today I am just compiling a bunch of shorter videos from my channel for any student who is reviewing your physical chemistry for an exam or for a test. The goal of this video is for you to review the examples that I've done already on this channel from the physical chemistry Atkins textbook. It is to help you in your journey through physical chemistry, whether you're about to take a test or whether you're doing a bunch of problem set. I wish you guys all the very best. Please enjoy the video. Salam. Today we're going to be working on the question. A sample of 255 milligrams of neon occupies 3.00 dm cubed at 122 K. Use the perfect gas law to calculate the pressure of the gas. So we're asked to calculate the pressure. We're told that the mass of the sample of neon is 255 milligrams, which is the same thing as saying 0.255 grams, because milligrams is the same thing as 1 times 10 raised to the power of negative 3 grams. So basically, you're going to move the decimal points 3 points to the left. So that's it. So that's mass of neon is going to be 0.225 grams. Then you have the volume of the sample occupies the container 3.00 dm cubed, which is the same thing as saying 3.00 liters. Use the perfect gas law to calculate the pressure of the gas. Well, before that, they told us the temperature, which is also T equals 122 Kelvin. So we're supposed to use the perfect gas law to calculate the pressure of the gas. We know that the perfect gas law, perfect gas equation is PV equals nRT. So pressure is going to equal nRT divided by V, and N, number of moles, is the same thing as saying mass over molar mass. So you end up having number of moles is going to be mass over molar mass times R times T divided by V. So that's going to be the pressure equals the mass of neon is 0.255 grams. So divided by the molar mass of neon. So I want you guys to check your periodic table for the molar mass of neon, or you can just Google it, whatever works for you. So that's the molar mass of neon is 20.18 gram per mole times the gas content is going to be 0.08206 liters atmosphere divided by mole Kelvin times temperature, which is 122 Kelvin, all of that information divided by the volume, which is 3.00 liters. So I'm going to cancel out the grams, cancel out the mole, cancel out the Kelvin, and cancel out the liters. Since I'm solving for pressure, it really makes sense that I want to have my answer in atmospheres. So now we have P equals 0.255 divided by 20.18 times 0.08206 times 122. All of this information divided by 3 atmospheres. So I wanted you guys to know that we're trying to solve for everything to be atmosphere. So you're going to input all of this information into your calculator, where you have, so we end up with 0.042169 atmospheres, and you have the 3 sig figs of this to be 0.0422 atmospheres. This is the answer to this question. Basically, we're done. So this is how you find the perfect gas law. The only tricky part of this question is the fact that we're not given the number of moles. Instead, we're given the mass, but we're also given the identity of the gas, which is neon. And from just knowing the identity of the gas and having the mass of the gas, we can find the number of moles, input it in our PV equals nRT perfect gas law, and we can find the pressure. Hopefully this has been helpful. If you have any question, put it in the comment section. Salam and welcome everyone. We're going to be solving the question on the screen that says, oh, a homeowner uses 400 meter cube of natural gas a year to heat a home. Assume the natural gas is all methane, and that methane is a perfect gas for the conditions of this problem, which are 1 atm and 20 degrees Celsius. What is the mass of gas used? Well, 400 meter cubed is them telling us that we're dealing with the volume, which is 4,000 meter cubed. We're told that we're dealing with methane gas, which is a natural gas, or basically which is a perfect gas, because we're dealing with a perfect gas question. So therefore, we're going to be using PV equals nRT, or any equation related to PV in it, or any equation related to PV equals nRT in this particular question. So make sure you put this equation, the perfect gas formula or perfect gas equation, in mind. We're told what the pressure is to be 1.00 atmosphere, and we're told what the temperature is to be 20 degrees Celsius. Well, in perfect gas equation, we never use the degrees Celsius. Instead, we have to convert to Kelvin. So temperature is going to be 273.15 plus 20, which is the same thing as saying 293.15 Kelvin. So we've gotten the temperature in kelvins, which is what we want. Now, we're told that what is the mass of gas used? Well, we don't know what the mass is because that's what we're trying to solve for. Now, looking at the equation PV equals nRT, we have to observe that we've been given the pressure, which is 1 atm. We've been given the volume, which is 4,000 meter cube. We've been given the temperature, which is 293.15 Kelvin. And we know what the gas constant is because the gas constant is a constant. So the only thing we actually do not have in this question is the number of moles. But since we're supposed to find the mass, and we don't have the number of moles, but we have the perfect gas formula, we have to first of all find the number of moles based on the parameters we have, and then use that number of moles to find the mass. So we have to now look at all our questions to make sure that all our units are proper. We have the temperature proper, the ATM proper, but we don't have the what they call it. We don't have the volume in the proper units because we would want to be able to solve this in dm cubed or in liters. Note that dm cube and liters are basically the same exact thing, right? So we know that we're dealing with 1 meter cubed. So I'm trying to compare 1 meter cubed to 1 decimeter cube. So 1 meter, we first have to remember that 1 meter equals what? 1 meter equals 10 decimeter, right? Hence, when we now decide to cube the 1 meter and cube the 10 decimeter, we realize that 1 meter cubed is the same thing as 10 decimeter times 10 decimeter times 10 decimeter. So inherently, 1 meter cubed is the same thing as saying 1,000 decimeter cubed. So that is how you basically do that. So now we're told that we have 4,000 meter cubed. So we're supposed to convert 4,000 meter cubed to whatever it is in decimeter. So we have 4,000 meter cubed equals what? Since we're trying to find what it is in decimeter, we're using the proportionality formula to be able to like work with this. So what that means is to tell you that we're just going to cross multiply because we've already determined that we know that 1 meter cube is always going to equal 1,000 decimeter cube. So that therefore 4,000 meter cubed equals what? So that's going to be the unknown x, the volume that we're trying to find in decimeter cube for 4,000 meter cube equals 1,000 times 4,000. And remember, we're dealing with meter, we're dealing in trying to solve in decimeter cube. So the meter cube here, the meter cube here, we cancel out and we have to retain the decimeter cube since that's what we're solving for. So what we end up with is 4 million decimeter cubed, which we can simply call 4 times 10 raised to the power 6 decimeter cubed, or 4 times 10 raised to the power 6 liters. One of the two is all right. Does that make any sense? Yep. So that is how you do it. So PV equals nRT. So now we have the volume to be, 4 times 10 raised to the power 6, 4 times 10 raised to the power 6 liters. So yeah, or DMQ, whatever you want to call it. So we have the P, we have the V, we have the R, we have the T. So N equals PV over RT. So which is pressure 1 atm times 4 times 10 raised to the power 6 liters divided by the gas constant, which is 0.08206. It's important for you to memorize the two gas constant that we have whenever you're dealing with perfect gas law. You have the first one, which is one I just had, 0.08206. So this is just a side note, liters atm divided by mole Kelvin. And then you've got the second one, which is 8.3145 joule divided by mole Kelvin, or 8.3145 kilopascal liters divided by mole Kelvin. So make sure you memorize both because there are going to be questions where it is better for you to use the one on the right, and there are going to be questions like in this case where it's better for you to use the one on the left. So that is it. So let's continue our work. So we have this times the temperature, which is 293.15 Kelvin. So we're going to cancel out the kelvins here. We're going to cancel out the atmosphere. We're going to cancel out the liters, leaving us to have just the mole, which is what we need, which is what we're solving for. So the number of moles is going to now equal 1 times 4 times 10 raised to the power 6 divided by 0. 0.08206 times 293.15. I'm rewriting this for all the students who may not be able to see clearly. So you import all this information in your calculator to get 66,279.5 mole. And I'm sure this is scary to you because you're used to seeing the mole being a small number. But let's not forget that they talked about the natural gas that is used to heat a home for a whole year. So this is the number of moles for the whole year. So I just wanted to make sure that that is remembered so that you're not scared thinking, why is the mole so large? It's not a small vessel or small container. You're literally dealing with an entire house being heated for a whole year. So yeah. So now we have the number of moles. From the number of moles, we're supposed to find the mass. So to do that, we have to remember the very common formula in chemistry, which is number of moles equals mass over molar mass. And in this case, we have the number of moles, which we have 166, 279.15. Since we know the identity of the gas, since we know the identity of the gas to be CH4, we can easily find the molar mass of CH4 by calculating it. We've got carbon, we've got hydrogen, we've got four hydrogens. So we have the atomic mass of carbon plus the atomic mass of 4 times that of hydrogen. So 4H, you can do that on the side notes. I'm not going to do that for you guys because it's just simple chemistry. Just solve for the molar mass. You're going to find the molar mass to be 16.04 gram per mole. That's what you solve. Remembering that carbon is 12 and hydrogen is 1. And since you're 4 hydrogens, that's 1 times 4, which is 4. So 12 plus 1 is basically 16. And the 0.04 comes from the fact that hydrogen is actually 1.01 gram per mole when you're solving for the atomic mass. So I don't need to like write all of that down. I can just say it. So to find the mass, we would just cross multiply and have the molar mass times the number of moles, and then we're going to get what the mass is. So the molar mass and number of moles is going to be us multiplying 16.04 gram per mole, okay, times the number of moles 166, 279.5 mole. We're going to cancel out the mole, and we're going to end up with 16.04 times 166,279.5, which is 2,667,122.4 grams, which when we do it and we basically approximate, we're going to end up using 3 sig figs. We're going to end up with 2.67 times 10 raised to the power of 6 grams. So the answer to this question is simply the mass is 2.67 times 10 raised to the power of 6 grams. That is the mass of gas used in the entire year to heat up the home. I wish you guys all the very best. If you have any question, please put it in the comment section. If you want me to be your personal tutor, make sure you email me at shuhabitutoring@gmail.com. I am a tutor for students all over the world. So if you need help in various STEM classes, whether you're in high school, middle school, and college, I am your go-to tutor. Salam and welcome everyone. Today we're going to be working on the question on the screen that says at 100 degrees Celsius, temperature 100 degrees, pressure 16.0 kilopascal, the mass density of phosphorus vapor, which is gas, is 0.6388 kilograms per meter cube. What is the molecular formula of phosphorus under these conditions? So we're trying to find the molecular formula of phosphorus atom or phosphorus vapor under these conditions. So that is basically what we're supposed to do. Since we're hearing the word vapor and we're seeing like the temperature and we're seeing the pressure, this is a perfect gas question. This is a type of format that they take. It's just that this is a more complicated one where you have to use your intelligence to solve it. So I require everyone to be very focused as I do this problem. So you've got temperature. Since we're going to be dealing with perfect gas, we can go from degrees Celsius to Kelvin. So we can say 100 degrees plus 273.15, and we end up having the temperature to be 373.15 kelvins. We have the pressure, and then we have basically the mass density, which is the same thing as just the density, which is just 0.6388 kilogram per meter cubed. What is the molecular formula of phosphorus under these conditions? Well, we first of all write out our perfect gas equation. We have PV equals nRT. We see that we've got temperature, we see that we've got pressure, we see that we have the gas constant because the gas constant is a constant. So no matter what, you're going to have in the question. And you can either use one of the two gas constants, which is 0.08206, or you can use 8.3145, whichever one works for you. And just keep in mind that the units of both gas constants are usually very different. So whatever is easiest for you and whatever the unit entails that you use is what you're going to use. I'm not going to write the units of both here just because there are multiple units that both forms can take. So you have all of this information, but you don't have the volume and you don't have the number of moles. But what you do have is the density. And we know that density equals mass over volume, right? And we also know that number of moles equals mass over molar mass. And we have a volume where we can substitute um, the information in terms of density and mass from this first information and boxing right here. And then we have the number of moles over which we can substitute mass over molar mass for, because we're actually even solving for the molecular formula. So we're going to do that. We see that density equals mass over volume. To write density and mass in terms of volume, we have divided by density. This is how you do it. So we have pressure, right, times volume in terms of mass and density. So that will be mass divided by density, okay, equals number of moles equals mass over molar mass. So mass divided by molar mass. So you have this here, and then you have R, and then you have T. So you go on to cancel out the mass to make our work easier. And what you end up with would be pressure divided by density equals R T divided by molar mass. So what this is telling you is that this is the new equation that is formed. But before we can use this equation, we have to make sure that everything is checking out, right? We've got pressure. We actually have a parameter for pressure, which is what we've given us 16.0 kilopascal. We have the density. We have the gas constant because it's a constant. We have the temperature. We actually do not have the molar mass. So in this case, we have 5 parameters that I've listed: pressure, gas constant, temperature, molecular mass, as well as density. But we have one unknown, which is the perfect way we like our questions whenever you're solving something. So to get this equation now in terms of M, we end up with RTD, so gas constant times temperature times density divided by pressure. And then we can input our information to this formula. Now, before we go on to solve anything further, I want to first of all show you guys that this density, we have it in the units of kilograms and meter cube. In chemistry, we tend to use our mass in terms of grams instead of kilograms, right? So we have to go take this 0.6 kilogram per meter cube, and we have to put it in a unit that is easy for us to use to solve this question. Well, in chemistry, we like to do grams rather than kilograms. And again, we just dealt with the question number of moles, and we have the molecular mass. Molecular mass is usually in grams per mole, not kilograms per mole. So we really have to go from kilogram here to gram. So that is that. Now we have meter cube. In chemistry, you can leave your volume in meter cube, but the best one is for you to leave it in dm cubed or in liters, because a lot of things are in this form. Not that you can't leave it in meter cube, but it's just easier and it's more common to have your stuff in either dm cube or liters. So we're going to go and make this liter. So we're trying to go from kilogram per meter cube to gram per dm cubed, or you can say gram per liter, because dm cubed is the same thing as liter. The only difference is dm cubed is used in the UK, liters is used in the US. That's literally like the major difference. Like when you're dealing with students in the British curriculum, they're going to be using more of dm cubed. If you're dealing with students in the American curriculum, you're going to be dealing with liters. So that is all. That is literally all. So yeah, that's all. So now we're going to go from kilogram to meter cube to gram per liter. So we're going to use dimensional analysis. So we're going to have 0.6388 kilogram per meter cubed times, okay, kilogram at the bottom and gram at the top. So we know that 1000 kilogram gives us, 1000 gram gives us 1 kilogram. So we can easily cancel out the kilogram and we have gram. Now we have to go from gram Sorry, now we have to go from meter cubed to dm cubed. So we have the meter cubed up top and we have the dm cubed at the bottom. We have to know this, that 1 meter, going back to basic math and unit conversion, is the same thing as 10 decimeter. Okay. So 1 meter cubed is going to be the same thing as 1 times 1 times 1, which is 1, then meter times meter times meter, which is just meter cubed. So you have 1 meter cubed. While 10 decimeter cubed is the same thing as saying 10 times 10 times 10, which is 1000, and dm cubed times dm cubed times dm cubed, which is dm times dm times dm, which is dm cubed. So you can see now that 1 meter cubed is the same thing as 1000 decimeter cubed. That's how you do it. So now we can now put that information here. So we are going to have 1000 decimeter cubed for 1 meter cubed. So that's how you do it. So now let's go on to finish solving it. By the way, we are just trying to get in the right units. We're not even actually started solving what we're supposed to solve for. So we have meter cube cancel meter cube. And we actually have 1000 at the numerator and 1000 at the denominator. So we cancel out this as well. So we end up with 0.6388 gram per dm cubed, or gram per liter. So you end up with 0.6388 gram per liter. And that is what we're going to input when we're solving this question. So now we're going to ignore all the stuff I just did at the bottom, and we are going to go back to the top to solve the actual problem that we're given. So 0. So what do you call it? So R here is going to be um sorry, I'm gonna just rewrite this. So we have RTD divided by P. So we're going to use the gas constant 8.3145 because it is the units match properly in this question. So kPa times liter divided by mole Kelvin times temperature 373.15 Kelvin times density 0.6388 gram per liter. All of that information divided by pressure, which is 0.16.0 kilopascal. So we're going to cancel out kilopascal, kilopascal, cancel out Kelvin, Kelvin, cancel out liters, liters. So you put all of this information in your calculator. But before we put it, let me just rewrite it down for any student that may be confused, because this is a lot of information. So 8.3145 times 373.15 times 0.6388. And then you have gram per mole. Okay, because that's what we're trying to solve for, molar mass, or yeah, molecular mass. And then you have divided by 16. So input this information, the numeric values, into your calculator, and you're going to end up getting 123.8695 gram per mole. Okay, now we've been successfully able to get the molecular formula. But what this question asks us to solve is for the molecule. Sorry, we've successfully been able to get the molecular mass. What this question asks us to solve for is the molecular formula of phosphorus, and phosphorus is an atom. Now we're dealing with phosphorus vapor, and they want us to find the molecular mass, molecular formula for phosphorus vapor. Well, now we have to understand that we have the molecular mass, which means that this phosphorus is actually a molecule, meaning it's not just one atom of phosphorus that is available. It could be 2, it could be 3, it could be 50, it could be more, because we're dealing with the molecular formula. So there has to be at least 2 atoms of phosphorus. So therefore, since we've solved for the molecular mass, we now have to go on to our periodic table, find the atomic mass. So here we have molecular mass. Let's call it mm now. And you have atomic mass. So go find in your periodic table the atomic mass of phosphorus. So looking at the periodic table, you will see that the atomic mass is 30.974 gram per mole. Are you seeing what's going on here? So now what you're going to do to find the molecular formula MF is that you're going to divide the molecular mass by the atomic mass to find the number of phosphorus atom in the phosphorus vapor molecule. So you end up with 123. Let me take this up a little bit. 0.8695 gram per mole divided by 30.974 0.974 gram per mole. We cancel out the gram per mole because we're not finding unit of anything. We're trying to find how many of it exist. So you put this information in the calculator. So the molecular formula becomes 123.8695 divided by 30.974. And we're going to get 3.999 as the unit. But because we have to approximate, because we cannot have it, we need a unit number. And to approximate this, we have the molecular formula to be 4. So what you're trying to ask you now is, what is the molecular formula of phosphorus vapor under the conditions given? So that means we're going to have 4 atoms of phosphorus for this question, and that is the same thing as having P4. So molecular formula is P4. So this is a molecular formula value. So the molecular formula for this question is P4. So that is how you solve this question. You can see how complicated it looks, but you have to use your intelligence to be able to solve this. So hopefully this has been very easy for you. So if you have any questions, put it in the comment section. If you'd like me to be your personal tutor for chemistry, math, and other STEM related subjects, make sure you email me at shahabitutoring@gmail.com. Salam and welcome everyone to my channel. Today we're going to be working on the question on the screen that says, at 500 degrees Celsius and 93.2 kilopascal, the mass density of sulfur vapor is 3.710 kilogram per meter cube. What is the molecular formula of sulfur under these conditions? So the first thing you have to do is to write out the parameters. We've been given the temperature in this question to be 500 degrees Celsius, which is the same thing as temperature equals 500 plus 273.15. So we can basically go from degrees Celsius to Kelvin to get 773.15 Kelvin. And we're given pressure to be 93.2 kilopascal. And this will stay the way it is. And we're also given mass density, which is just simply density, to be 3.710 kilogram per meter cubed. So we're now asked to find the molecular formula of sulfur under these conditions. So the first thing we have to do is to remember that this question is taking the form of a perfect gas. Hence, we're going to use the perfect gas equation PV equals nRT. So from this, you can see that we've been given the pressure, we've been given the temperature, but we've not been given the volume, neither have we been given the number of moles. But we also know the gas constant, because since it's a constant, we always know the value. So depending on how the question is, we can either use 0.08206 or 8.3145. And I'm not going to write the units for both of them, because depending on what the question is, the units would vary, but they have to be these two values no matter what. So this is just something I just feel like I should put on the side. But we have like two unknowns in our question. And one thing about solving in chemistry, math, or just doing calculations, you can't have two unknowns. It messes up the question. But we also know that we've been given another parameter, which is density. And just remembering basic physics, chemistry, or basic science, we know that density equals mass over volume. So therefore, we have a volume right here, and we would write this volume that we have right here in terms of mass and density. And to do that, we end up getting volume equals mass divided by density. So we're going to substitute this volume here. And then we also have N, which is number of moles. And we also know that number of moles is the same thing as mass over molar mass. So we have the molar mass, we have the mass, and we write that in terms of number of moles. So we don't have to do any recalculation here. So next thing we do is just substitute the information. So we have P times V in terms of mass and density. So that will be M divided by D equals number of moles in terms of mass and molar mass. That will be mass divided by molar mass. And then we have R, and then we have T. So we cancel out mass, we cancel out mass. What we end up with is P divided by D equals RT divided by molar mass, or mm. Now, if we look at the question, we see that we've got the pressure, okay, we've got the density, okay, we know the gas constant, okay, and we've got temperature, but we don't have molar mass, which works for us because we have 5 parameters in total. We have 4 known parameters, like the values of 4 parameters, and we have 1 unknown, meaning we're going to be solving for the molar mass mm. So that would just mean rewriting all of this equation. P over D equals RT, RT divided by molar mass. Rewriting this equation in terms of molar mass, we're going to end up having RTD divided by P. So basically, the gas constant times the temperature times density, all of that information divided by pressure. And we're going to now input the parameters for each one of them. We're going to input the parameter for pressure, for density, for temperature, as well as the gas constant that works well for this question. But before we go on to do that, we have to break the information down. You see that the density, which is 3.710 kilogram per meter cubed. We see that it is in kilogram. We know that molar mass in chemistry is usually gram per mole. And basically, majority of the calculations of math in chemistry, if not all of them, majority actually, not all of them, they tend to work with grams. They don't work with kilograms. So that is teaching us that because of we're doing chemistry, we have to convert from kilograms to grams. That's the first thing you have to know. Then secondly, we have meter cubed, and we can leave our information in meter cube, but what is more common in chemistry is to have dm cube instead of meter cube, because it's just easy for calculation, and it's more common to have dm cube instead of meter cube. So what this is teaching us now is that we have to go from having kilogram per meter cubed, right, per meter cube, to gram per dm cubed, or you can also say gram per liter, because dm cubed, right, is the same thing as liter, right? Dm cubed is literally the same thing as liter. It's just that dm cubed is used more in the UK, and then liter is used in the US. So depending on what curriculum you are using, you can see that some places are going to use dm cubed, some other places would rather use liters. So just put that in your memory. So now we're going to change the units of the value of density. So we've got 3.710 kilogram per meter cubed. And we're going to try to use the dimensional analysis to change it to gram per liter or gram per dm cube. So we know that kilogram will be at the bottom and grams will be at the top. So we have to remember that 1 kilogram always gives us 1,000 grams times, we're going to have the meter cube up top and we're going to have the dm cube at the bottom. And we know that 1 meter cube always gives us 1,000 dm cube. And the way you do it is just remembering that 1 meter equals 10 decimeter. Hence, 1 meter cubed, which is 1 times 1 times 1, which is 1, and meter times meter times meter, which is meter cubed. The same way you're going to have this 10 decimeter, all of that information cube, which is just going to be 10 times 10 times 10, which is just 1,000, and dm times dm times dm, which is dm cubed. So that's how we have 1 meter cube equals 1 decimeter cubed. If that makes any sense. I believe it does. So that's the thing you have to know. And that is it. Like, that is literally it. So we go on to cancel out the kilograms and cancel out the meter cubed. And what you end up with is gram per decimeter cube. But the thing now is we have a 1,000 up top, we have a 1,000 at the bottom. So we just simply cancel that out and we write the new unit conversion of the value to be 3.710 gram per decimeter cubed, or 3.710 gram per liter. So that is how it's done. So that is what we're going to use now to that's basically what we're going to do now. So yeah, now we've done 3.710 gram per liter. Now we can input this information into the question, sorry, into the equation at above. So RTD is the same thing as having 8.3145 K, which, and we have the kilopascal liters divided by mole Kelvin. That is the unit for the gas constant. And you've got temperature to be 773.15 Kelvin times the density to be 3.710 gram per liter. All of that information divided by the pressure, 93.2 kilopascal. So we're going to cancel out the liters. We're going to cancel out the Kelvin, and we're going to cancel out the kilopascal. And what we're going to end up with is just having the gram. sorry, the gram right here and the mole right here. So let me just rewrite everything. Molar mass equals, just rewriting anything that hasn't been cancelled out so everyone understands. So you have 8.3145 times 773.15 times 3.710 divided by 93.2. And then you have gram per mole. Because of course we want the molar mass to be in gram per mole. So we input all of this information into a calculator to get 255.893 gram per mole. Now, the question asks us to find the molecular formula of sulfur under these conditions. Molecular formula is of sulfur is just telling us that sulfur has more than one atom. Hence, sulfur is a molecule. So sulfur could end up with two atoms. Sulfur could be six atoms. Sulfur could be 12 atoms. They want us to be able to write the answer in this form where we're going to be dealing with the sulfur as a molecule, but it needs to have a formula. Now, the way you're going to do that basically is for you to use the information with sulfur. We see that the molecular mass is 255.893 gram per mole. Then we have to remember that this is just the molecular mass of sulfur. We have to remember that sulfur itself is an atom, right? And the atomic mass for sulfur, meaning one sulfur's atomic mass, an atom, which is one, molecule, which is more than one, right? The atomic mass of sulfur, we have to go onto our periodic table. And when you check it, you're going to see that it is 32.065 gram per mole. So the molecular formula is just going to be the unit, basically the unit of the molecular formula is going to be the molar mass divided by the atomic mass. So you have 255.893 gram per mole divided by 32.065 gram per mole. So you cancel out the gram per mole, cancel out the gram per mole. So you have the molecular formula unit basically to be 7.98, and 7.98 approximately when you're dealing with units is just 8. So the sulfur atom or the sulfur molecule is just going to be S8. So basically, in this molecule of sulfur, there are 8 atoms of sulfur in this S8 molecule. So that is the molecular formula. The molecular formula is S8. Wish you guys all the very best. If you have any questions, please put it in the comment section. Salam and welcome everyone to my channel. Today we're going to be working on the physical chemistry question that says a perfect gas undergoes isothermal compression, which reduces its volume by 1.8 dm cubed. So from the first sentence, we know that it is an isothermal compression, meaning the change in temperature is zero because isothermal means constant temperature and compression means a reduction in volume. So the volume is going to decrease, right? So meaning the initial volume, meaning the volume at the beginning is greater than the volume at the end. So the initial volume is greater than the final volume. So and it reduces its volume by 1.8 dm cubed, meaning the change in volume is 1.80 dm cubed or liters. Dm cube and liters mean the same thing. The final pressure and volume of the gas is the final pressure and volume of the gas are 1.97 bar. So final pressure, which is PF, is going to be 1.97 bar. Let's just stick to writing this as dm cubed since we have another volume saying dm cubed. But just know that dm cube and liters are literally the same thing. I believe dm cube is used in the UK and liters is used in the US. So final pressure is 1.97 bar and the final volume is 2.14 dm cubed. If you remember correctly, I mentioned that the initial volume is greater than the final volume, and then we have the change in volume to be 1.8. So that just means that our initial volume, we can solve for it here, is going to mean the final volume plus the change in volume. And our initial volume is going to be final volume 2.14 dm cubed plus 1.8 dm cubed to get 3.94 dm cubed. You can see how the initial volume is greater than the final volume. That's to tell you that it's really a compression. So calculate the original pressure of the gas. So we're supposed to solve for initial in bar. So that's the first question. And then in torr. So what we're just supposed to do is to remember that since this is an isothermal reaction, or isothermal compression, and we know the change in temperature is the same. Sorry, the change in temperature is zero, meaning the temperature is the same all throughout the entire reaction or compression process. It's important for you to know that we would use the formula P initial times V initial equals P final times V final. You know, not regularly we have PV equals nRT, right? The temperature in this case is going to be the same. So even if you put it and do PV equals nRT for one and then PV equals nRT for two, it wouldn't make any sense because the temperature is the same. So it's going to just simply cancel out if there was a P initial, V initial, N initial, and T initial. So the temperature will cancel out because the T initial and the V initial is basically the same thing. The number of moles will cancel out because they did not tell us the number of moles increased or decreased, or there was a hole in the container where the number of moles removed. The constant is always going to be the constant. So the number of moles, the gas constant, the temperature, all are going to be the same. So you can simply remove them from the equation. So you'll be left with P initial, V initial equals P final, V final, which is what we have here. I'm just teaching you how we got to this point. This is like the quicker method. If you want a better understanding of it, then you should go back to your textbooks and read about this particular, or you read about combined gas law. It's going to teach you how to work with P initial, V initial is equals to P final, V final, and how you get to those points. I've just given you like a short summary. So we have our P initial to be, we don't know, that's what we're solving for, so we're going to just simply have P final times V final over V initial. So that's going to be P final, we know that to be 1.97 bar, times V final to be 2.14 dm cubed, and our V initial to be 3.94 dm cubed. We can go on to cancel out the units and then input all of this information in the calculator, where P initial is going to be 1.97 times 2.14 divided by 3.94, and then you have a bar right here. So you input this information in the calculator to get 1.07 bar. So that is it. So that's the P initial. That's what you get for the P initial. Now we're asked to solve it in terms of torr. Now it's important for you to know something, that 1 ATM, because anytime you're given a unit conversion question, you have to either memorize it or you have to memorize how everything is in relation to atmospheres, which is what I do. So 1 atmosphere is the same thing as 1.01325 bar. And then 1 atmosphere is also equal to 760 torr, which torr and mmHg are basically the same thing. So this is just teaching you that 1 atmosphere, I don't know what's, yeah, this is just teaching you that 1 atmosphere, since it's equal to both, so that means 1.01325 bar is the same thing as 760 torr. So you just use the knowledge of comparison of what you already know, which is 1 atmosphere. And I like to use 1 atmosphere because it's just one. It doesn't have like a big number in front of the units. It's just one. So this is how you do it. So now I'm going to teach you, we're going to solve this by, we're going to solve this unit conversion without using dimensional analysis. We're going to use proportionality. So which means that 1.10325 bar equals 760 torr, but we are asked to solve for 1.07 bar. So that means 1.07 bar would give you what? Like, what is it going to give you? What is it going to give you? You don't know. That number that we don't know is an unknown, so we can denote it as X, and then we can just do simple math and just simply cross multiply. So that would just mean, rather than writing the entire thing through dimensional analysis, you can do this quick method. So that would just mean X, write your unknown, times 1.01325 bar equals 760 times 1.07 and then bar and torr. Like basically, I'm just separating the units from the information. So the X unknown is going to equal, first of all, before we go on to solve it, you can make your work easier by just simply canceling things out. You can cancel out bar, since we're going to solve it in torr anyway. So let's go up a little bit. We're going to end up with 760 times 1.07 torr divided by 1.01325. And when you solve this, x is going to equal, it's going to equal 802.566 torr. And in three significant figures, which is what we've been having the information so far, x, the unknown, is going to give us 803 torr. So to answer your question, finding the initial pressure in torr is simply 803 torr. And the initial pressure in bar is going to be 1.07 bar. So if we zoom out, you can see all of our work, and you see that we've answered all the questions correctly. And this is basically our answer. We have first of all broken things down, solved for the initial pressure using the combined gas law. And when we found it in bar, we were now able to do unit conversion to find it and determine the initial pressure in torr. So if you have any questions, please write it down in the comment section. Salam and hello everyone. Today we're going to be working on the fifth question in the series of physical chemistry slash thermodynamics, and we have this particular question on the screen that says a perfect gas undergoes isothermal compression. So isothermal is just letting us know that we're dealing with constant temperature. So that means the final temperature and the initial temperature are going to be the same. There's not going to be change in temperature, would just equal zero. So there's no change in temperature. And then the word compression says lesser volume. So that means the final volume. So the final volume is going to be less than the initial volume because there's a decrease in volume. Okay, which reduces its volume by 2.20 dm cubed. So that means change in volume is simply 2.20 dm cubed, which is the same thing as 2.20 liters. So I'm just going to, just going to do this right here. So we have space to do all of the problems. So now they gave us the final pressure, P final, and the final volume, so V final, are 5.04 bar. That's for the pressure, the final pressure, and 4.65 dm cubed, which is the same thing as 4.65 liters. Calculate the original pressure. So we're asked to find P initial. Now, the first thing we have to do before we go is to determine what VI is, so the initial volume, before we can go on to solve for the initial pressure. Well, the initial volume is just going to be whatever the final volume is. And so the final volume, which is 4.65, so final volume, right, plus the change in volume. This is just simply us remembering that since this is a compression situation, we're going to have an increase or higher volume number for the initial volume. So it's going to be a plus sign, right? So you already know, like, the situation here, the final volume is less than initial volume, so it's going to have a plus sign, plus the change to the final volume is going to give you the initial volume, since we're dealing with a compression basically. So plus change in volume, which is 2.20 liters. All of them are in liters here. So initial volume is going to be 4.65 plus 2.20 is 6.85 liters. So that's the answer for that. Now, because we are told that we're dealing with constant temperature, we know that we're going to deal with Boyle's law. We also know the number of moles is going to remain constant. They didn't say that here, but they did not tell us about a change in number of moles. So we're going to assume that's constant as well. So what we're just going to do here is for us to use the Boyle's law formula, which is P initial times V initial equals P final times V final. So yeah, that's it. So we're just going to like input what we have. We have P initial is what we're trying to solve for. So we're going to rewrite the formula to be P final times V final divided by V initial. So that's going to be P final is 5.0 bar, okay, times V final, which is 4.65 liters, divided by V initial, which is 6.85 liters. So we're going to cancel out the units, and we're going to just have P initial to be 5.04 times 4.65 divided by 6.85. So what we end up with is just 3.42 bar. So the initial pressure is going to be 3.42 bar, or 421 bar. You can also have that. But since our question is in three sig figs, we're just going to round up. So this is not actually equal to sign. This is estimate. It's actually longer. It's 3.42131387, but approximately 3.42 bars. So we've answered the first part of the question. Second part of the question is asking us to do it in atmosphere. So I'm just going to write that. So question 2 is asking us to do it in atmosphere. So that's just involves a change in units. So if you've not watched my change in units video, and make sure you do watch it. I think it's going to be very important in order for you to solve this. But let's move on. Sorry, what's going on? Okay, so let's move on. Let's do it here. 3.42 bar, okay, times units conversion formula. We have to have bar at the bottom at the denominator so that the units for bar can cancel, and we have to have atmosphere up top. So we're just going to put the value of that compares atmospheric pressure units to bar units, right? So regularly we have one atmosphere always equals 1.01325 bar. So we're just going, since we know this is it, this is a standard unit conversion values. We're just going to put that here. So 1 ATM and then 1.01325. And then we go on to do the basic math, cancel out the bar. And so we end up with 3.42 times 1 divided by 1.01325 atmosphere here. So we end up with the original pressure P initial in atmosphere to be, put that in your calculator, 3.42. You can actually use the value 3.421 like and all that before it becomes 3 sig fig. So you can use 3.421 divided by 1.01325. We can do that instead, since at that particular point we have not, since we're trying to get in 3 sig figs for the atmospheres, and that's how you do proper calculations, by the way. You don't do 3.42 times 1. I'm just showing you this using the estimated value. So 3.42131,387 divided by 1.01325. So you got 3.376574. So in P atmospheres, so approximately the initial pressure is going to be 3.38 atmospheres. So we've gotten the answer in bar, which is 3.42 bar, and we've gotten the answer for initial pressure in atmospheres to be 3.38 atmospheres. I wish you guys all the very best. Salam and hello, everyone. So today we're going to be working on the question on the screen that says, um, a vessel of volume 22.4 dm cube contains 2.0 mole of H2 gas and 1.0 mole of N2 gas at 273.15 Kelvin. So the first thing I have to do is to just basically write out what you're given. You've got the volume to be 22.4 dm cubed, which is the same thing as saying the volume is 22.4 liters, because dm cubed, right, is also equal to liters. So I'm going to make this a column of its own, make another column. So you have this to be this. Then they told you the number of moles of H2 gas is 2.0 mole. So H2 gas is 2.0 mole, right? And the number of moles of N2 gas is I apologize, is 1.0 mole. So I need to write information out so no mistake whatsoever. And then you have the temperature to be 273.15 Kelvin. And you're asked to determine the mole fraction of each component. So what they're just trying to say is the mole fraction of each one of the gases, both the N2 gas and the H2 gas. So you have the mole fraction to be, the formula is the cursive X of, say, the H2 gas, which is the mole fraction of, just basically mole fraction, okay, of H2, is going to be, the formula would be the number of moles of H2 gas in the mixture divided by the total number of moles of the mixture. So in total, so that's just simply us writing 2.0 mole divided by the adding the number of moles for both N2 gas and H2 gas. So that would be 1.0 mole plus 2.0 mole. And that's what you get. So that would just be the mole fraction of H2 would be 2 mole divided by 3 mole. And you cancel it out. And then what you end up with is 2 over 3, which is something as 0.667. Now we're going to replicate this for nitrogen gas. So NX2, that would be the number of moles of N2 gas divided by total number of moles, which is 1 mole of N2 gas divided by 3 mole, which is the total number of moles. So what you end up with is cancel, cancel. So that would be X N2 equals 1 over 3. Or you can just simply say X N2, so the mole fraction of nitrogen is 0.333. So that's it. And that's the answer. We've gotten that first one. Now, the second one, we're asked to find the partial pressures. Now, partial pressure is from the law of Dalton's law of partial pressures that just says the total number or total amount of pressure exerted in a mixture is just the sum of each individual gas component's pressures. So, like, say in this case, the total pressures in a mixture will just be the pressure of N2 gas as well as the pressure of H2 gas added together. So the sum of this pressure is going to give us the total pressure exerted by the mixture. So this is called Dalton's law of partial pressures. Now, that is what we need. So that means basically to find the total pressure or each one of these individual, we can use this formula. But there's also something else you need to know, right? Because it's chemistry. It's always something else to know. So you have the partial pressure, for example, of nitrogen divided by the total pressure of nitrogen is actually going to give you the mole fraction of nitrogen. So it's important for you to know that if we even want to find the mole fraction of nitrogen, we can just divide the partial pressure divided by total pressure. But since that is not the case here, where we are trying to find the partial pressure, so this is just going to be the partial pressure of nitrogen is going to equal X, so mole fraction of nitrogen times the times the total pressure. And this is what we do. And we'll do this exact same thing too for hydrogen gas. So I just wanted you guys to know the importance of this formula because it's still going to come into play. Now, because we don't know what the partial pressure is, we don't know what the total pressure is, we cannot move on and we have to solve one of the two and combine it with the partial pressure of nitrogen to get the last one. But we don't know what it is, so we're just going to use the information we have. If we go back to our work, we see we have the volume, we see that we have the temperature, and we see that we have the total number of moles, which is the addition of the mole components amounts. So that means we can use the good old ideal gas formula, PV equals nRT, where in this case, the P is the total pressure and the N, the number of moles, is the total number of moles. So what we actually have, rewriting this, is to find the total pressure, we have PT subscript. It goes in NT RT divided by V. So that is what we do. So the total pressure becomes the number of moles. We have that to be total number of moles, 3.0 mole, right? Times the gas constant, 0.08206 liters ATM divided by mole Kelvin times 273.15 Kelvin. So all of that information divided by the volume, which is just 22.4 liters. So we start off, I like to do this all the time, cancel out all of the units so I know what I'm working with. Mole cancel out, Kelvin cancel out, liters cancel out. So we only have ATM, which matches the fact that we're finding pressure. So that means we're on the right track. So I'm just going to rewrite what we have. So P total is just going to be 3.0 times 0.08206 8 times 273.15. Remember atmosphere, since that's the only unit that remains, divided by 22.4. So we input this in the calculator to get 3.00197 atmosphere. So P total will approximately be 3.0 atmospheres. So that means the total pressure, let me rewrite that. P total is just 3.0 atmospheres. Now that we have the total pressure, we can do what we would like to do to be able to get the answer. So we have the mole fraction. Looking at the formula I taught you previously, remember, you have the partial pressure of N2 is going to be the mole fraction, that is just how it works, of N2 times the total pressure. And then in this case, the partial pressure of H2, the second component, is the mole fraction of H2 times the total pressure. So we can use each one of this formula to get it. So let's use the partial pressure of H2. I like to use that, equals the mole fraction of H2 times PT. So that would be partial pressure of H2 is just going to be, the mole fraction of H2 is 0.667, like what we solved for right here. Okay, that times the total pressure, which we solved for to be 3.0 atmospheres. So what we end up with is pH2 equals, not times, I apologize, equals 2.0 atmospheres. And that is the answer to this one. The second one is just simply remembering that the total pressure, remember this formula here? Total pressure equals to the sum of the each individual pressure component. So Pn2 plus pH2. So we can rewrite the formula to be Pn2 equals, right, P total minus pH2. So that will give you P total, Pn2 to be, P total is 3.0 atmosphere minus that of H2, which is 2.0 atmosphere. So the pressure of nitrogen, the partial pressure of nitrogen is just 1.0 atmosphere. So now we have determined the mole fraction of each component successfully. We've determined the partial pressure and we've determined the total pressure. I wish you guys all the very best. Make sure you watch all the videos on this series for physical chemistry. The textbook I'm using is the Oxford Atkins Physical Chemistry book, the 11th edition. I wish you guys all the very best. Salam and hello everyone. Today we're going to be working on the question on the screen, and this is another physical chemistry question that says a vessel of volume 22.4 dm cube contains 1.5 mole of H2 gas and 2.5 mole of N2 gas at 273.15 Kelvin. Calculate the mole fractions of each component, their partial pressures, and their total pressure. So the first thing you have to do is for you to basically to write out the parameters that we're given. We have the volume to be 22.4 dm cubed, which is the same thing as 22.4 liters because dm cubed equals liters. The next thing we are given is the number of moles of the H2 gas is 1.5 mole, and the number of moles of the N2 gas is 2.5 mole, and the temperature of the vessel or temperature of the gases in the vessel is 273.15 Kelvin. So we're asked to find the mole fractions of each component. So now mole fraction is just the number of moles of the one of the components, say H2, divided by the total number of moles. So the number of moles of one of the components, for example, H2 divided by the total number of moles. So you get the mole fraction, which is just signified by or the symbolized by the cursive X and then the subscript of the symbol of the component or the gas. So XH2. So that's how you would get the mole fraction. We can also replicate this with nitrogen. But before we go on to do that, let's start with solving or by solving this. So you have the mole fraction of H2 gas to be the number of moles of H2, 1.5 mole, divided by the total number of moles, which is just the addition of both the moles of the number of moles of H2 and the number of moles of N2 gases. So you have 1.5 mole plus 2.5 mole. So basically, it's just like NH2 divided by NH2 plus N2. So that's just basically what's happening. We're adding the number of moles of N2 and H2. So XH2, the mole fraction of H2 gas, is 1.5 divided by 4. So mole. We are going to cancel out number of moles because that's how we do it in chemistry to get 1.5 divided by 4, which is just simply 0.375 for the mole fraction. Now, the second one is to find the mole fraction of N2 gas. So that would be XN2, which is the number of moles of N2 gas divided by the total number of moles, or the N2 plus NH2. Just basically what we did, we're just replicating the same thing here. So number of mole of N2 gas would be 2.5 mole, divided by 4.0 mole. And what we end up getting is, when we put this in the calculator, we get 0.625. So now we have both information. Now we're asked to find the partial pressures and the total pressures. Partial pressures means the second one. Now it's important for you guys to know this. Whenever you're given a question that involves partial pressures and total pressures, that means you're going to be dealing with the Dalton's law of partial pressure, which is just the total pressure of a particular mixture is the sum of the individual pressures exerted by each of the gas components. So in this case, it's going to be the total pressure equals to the partial pressure of H2 gas plus the partial pressure of N2 gas. If we had 5 different gases, you're just going to add up the individual pressures of the 5 gases to get the total pressure. So that's something you need to know. Another thing you need to understand is the partial pressure of each one of these gases divided by the total pressure would give you the mole fraction of the gas component in question. In this case, that's H2 gas. So this is another way of solving it. That means in order for us to find the partial pressure, we have to know the total pressure, or in order for us to find the total pressure, we have to know the H2 gas. But in this particular case, what we have is the mole fraction, but we don't have the total pressure, we don't have the partial pressure. So it causes a little bit of stress in the work. So what we have to do is to think outside the box and think within the information that we're given. So what we have to do in any case is to remember what we're given and what we've solved for in the question. We've been given the volume. We've been given the total number of moles by adding up the individual numbers of moles. We've been given the temperature. So this is just calling us to do the ideal gas formula to solve for the total pressure first before we can go on to solve the partial pressure. So that's going to be the total pressure equals the number of moles for all of the mixture. So the total number of moles times R times T divided by volume. Since we're solving for total pressure, we can rewrite the formula as this. And we're just going to input the information we have. Let's pick a different color. Let's do green. So PT is going to equal number of moles, total number of moles is 1.5 for 2.5. So that's 4.0 mole times 0.08206 liters ATM divided by mole Kelvin times the temperature, which we have to be 273.15 Kelvin. All of this information divided by the volume, which is 22.4 liters. So simple thing is just for us to cancel out all of the units and go on from there. So we have liters cancel liters, mole cancel mole, Kelvin cancels Kelvin. So we end up with rewriting what we have. We have PT equals 4.0 times 0.08206 times 273.15, and we have ATM. Since we're solving for pressure, let's not forget our ATM, because that's like the only unit that remains, and we're supposed to get our units for pressure to be atmospheres. All of that information divided by 22.4. So input this information in the calculator to get 4.00. So pure pressure will be 4.0026, which is approximately 4.0 atmospheres, which is going to be the answer to the total pressure. Now we've gotten the first question, the mole fractions of each component as well as total pressure. Now we can do the simple math and all the formulas we've learned so far to find the partial pressures. So partial pressure, let me use a different color just because we've been overusing blue. So let's pick a color. Let's use orange. So you have the total pressure, sorry. So you have the partial pressure of H2 gas to be the mole fraction of H2 gas times the total pressure. Remember how I told you pH2 divided by P total equals the mole fraction of H2? This is how you can like do this as well. So this is basically a formula. Well, we rearrange that formula by solving everything and equating it to the partial pressure of hydrogen to get the formula that we're about to use here. So we have the pressure of hydrogen gas to be 0.375 times the total pressure of 4.0 atmosphere. So pressure of hydrogen gas is 1.50098 atmospheres, which is approximately 1.5 atmospheres. That's what we get. And remember that I explained Dalton's law of partial pressure previously to be total pressure equals the sum of the individual pressures exerted. So that would be Pn2 plus pH2. Hence, Pn2 is just going to be the total pressure minus the pressure of H2 gas that we just solved for. So that would be Pn2 is going to equal P total, which is 4.0 atmospheres, minus pH2, which is what we just solved for, 1.5 atmospheres. So Pn2 ends up being 2.5 atmospheres. So the partial pressure of nitrogen is 2.5 atmospheres. I wish you guys all the very best. I hope you've understood something or more than something. Salam and welcome everyone. So we have the question: a vessel of volume 22.4 dm cubed, which is the same thing as saying 22.4 liters, contains 2.0 mole of H2 gas and 1.0 mole of N2 gas, which is the same thing as having the number of moles of H2 gas is 2.0 mole and the number of moles of N2 gas is 1.0 mole at 273.15 Kelvin. So the temperature is 273.15 Kelvin. We're asked to calculate number one, the mole fraction of each component, number two, their partial pressures, and number three, the total pressures, right? Right, the mole fraction of each component is important for you to know that when somebody's talking about mole fraction, it's just simply what you know about fractions, right? A part of the information divided by the whole. So if you're asked to find, for example, the mole fraction of component A, is just simply the number of moles of component A divided by the total number of moles contained in the mixture. So in this particular vessel, well, if we're asked to find the mole fraction of each component, hence the mole fraction of, say, H2 gas, it's going to be simply, we're asked to find the mole fraction of H2 gas. It's going to simply be this symbol, and you put a subscript for H2, and the number of moles of H2 divided by the total number of moles. And in case of N2, is just simply us writing the mole fraction symbol of N2 and then subscript N2, number of moles of N2 divided by the total number of moles. And we're just going to substitute the information from our parameters and calculate. So now that we've gotten that concept down, we're going to start solving. So I'm going to actually show you what to do. So you have the mole fraction of H2 gas, the first component is simply going to be the number of moles of H2 gas divided by the total number of moles. So the total number of moles, which is for us to now write, the number of moles of H2 gas is 2.0 mole divided by the total number of moles, which is 2.0 mole. Okay, that's the one for the H2 plus 1.0 mole, which is the one for the N2. So this is the number of moles of H2 right here and the number of moles of N2. So this is how you solve mole fraction. You add up all of the moles that are in the particular questions together to get the total number of moles, and that's going to be the denominator of um is going to be the denominator of the fraction, while whatever you're solving for, the particular component you're solving for, is going to be the numerator, right? So that's what you do. So now the mole fraction of H2 is simply going to be 2 divided by 3 because, of course, the moles will cancel out. So the moles all cancel out. Since we're dealing with fraction, we can have units. 2 over 3 is simply using 0.667. So this is the answer to this particular mole fraction. Now we're going to be solving for the mole fraction of N2, which is going to be this. So the number of moles of N2 gas divided by the total. The number of moles of N2 gas, that will be 1.0 mole divided by 3.0 mole. We cancel out the mole. That's going to be 1 over 3. So the x2 is going to be 1 over 3, which is the same thing as 0.333. So basically, it's important for you to now know this, that we've gotten the first part of the question. So for any of you who do not know, mole fractions always add up to 1 for each one of for every single mixture you're given. So the mole fraction of each component, when they are all added up together, they're always going to give you 1. In this particular question, you have just 2 components, right? We have the mole fraction of H2 and then we have the mole fraction of N2. This information always has to add up to 1. And that's the way for you to check your answer. So we have 0.667 plus 0.333. If you add that up, you see that it's going to be equal to 1. Which also means that if you solve for the mole fraction of one component, you can just subtract that information from 1 to get the answer. So like how we have the mole fraction of H2, could have just simply done 1 minus, to be able to find the mole fraction of N2, could have just simply done 1 minus the mole fraction of H2. So the mole fraction of N2 would have been 1 minus 0.667, and we have 0.333. So that's how like you do it. So I'm just letting you guys know that if you're given 8 components or 8 gases in a particular mixture or in a particular container, and you're asked to find the mole fraction of where you're asked to find the mole fraction of each one of those components, just know that when you add the mole fraction of all the 8 components, they all have to add up to 1. So that's just one thing you need to know. So now we've handled that. Now we're going to the partial pressures question, which would be which would require us to use the formula PV equals nRT. So the partial pressure, for example, of H2 is going to be pH2 times V volume equals the number of moles of H2, R, which is a gas constant, so it's going to remain constant, and then temperature, which is always going to remain constant. So the temperature of one particular component is not going to be different from another particular component, just like the temperature of water, H2O, boiling point is 100 degrees Celsius, right? Nobody's going to say that the temperature of H2, it has to be separate from the temperature of O2. If it's a mixture, they have one volume and one temperature. It's the only thing that can be different for each one of the gases in a mixture or anything can just be the pressure and the number of moles. Those are the only things, like the volume, the gas constant, and the temperature will always be consistent. So I just wanted everyone to know that. So now we're asked to find the partial pressure. So that would be P of the partial pressure equals NH2 RT divided by V, which is pH2. So NH2 is for us to remember that we've written down the parameter for this, that's 2.0 mole times the gas constant that we're going to be dealing with here. Well, the gas constant we're going to be dealing with, we're going to pick the easier gas constant, which is just 0.08206 liters ATM divided by mole Kelvin times the temperature, which is 273.15 Kelvin. Basically, the parameters we've written here, all of that information divided by the volume, which is 22.4 liters. So we're going to cancel out all the units. We cancel out the mole, cancel out the Kelvin, cancel out the Kelvin, cancel out the liters, cancel out the liters, because the whole point of us using solving for this is for us to determine the pressure. So we have this P H2 is just us inputting all of this information into that calculator. So that would be 2.0 times 0.08206 times 273.15 divided by 22.4. And all of that has ATM because we couldn't cancel out ATM since we're solving for pressure. So yeah, all of this information would be 2.0013 ATM. And when we do the three sig figs question or two sig figs, whatever you want to call it, let's do two sig figs because we have 2.0 mole as two significant figures and it's the lowest out of this question. So we end up with the pressure of pH2 to simply be 2.0 atmosphere. So this is the answer to this question, 2.0 atmosphere. Now we've done the partial pressure for one. We're going to go on to solve the partial pressure for the other one, which is for the one for N2. So using the same formula, we have N of the number of moles of N2 gas times R times T divided by V. So this would look like the number of moles of N2 according to the question is 1.0 mole. If you go back to the parameters, that'll be 1.0 mole times 0.08206 liters ATM divided by mole Kelvin times 273.15 Kelvin. All of that information divided by volume, which is 22.4 liters. So everything, you cancel out everything. And mole, mole, Kelvin, Kelvin, liters, liters. And so PN2 will simply be 1 times 0.08206 times 273.15, and then you have atmospheres, all of that information divided by 22.4. So when you solve this information, you get 1.0007 atmosphere, and using two sig figs, we're going to end up with 1.0 atmospheres for the pressure of N2 gas. So that is how you solve. Now we go to the third part of the question that says we should determine the total pressure. So determine the total pressure, this isn't a lot of work. You can solve it in two ways. I'm going to show you the main way for you, the quick way, and I'm going to show you another way that is not as quick, but it's like teaches you the concept. So to find the total pressure would just be adding up the individual pressure. So the pressure of the N2 gas and the pressure of the H2 gas. So total pressure would end up being pressure for the N2 gas, we know that to be 1.0 atmosphere. The pressure for the H2 gas, we know that to be 2.0 atmosphere. So the total pressure is going to simply be 3.0 atmosphere. And that is the answer to this question. Now, the concept based one I wanted to teach you is for you to understand that anytime that you're solving for total pressures and you have the mole fraction down, so say you have the mole fraction of H2 and you also have the partial pressure for H2, you can find the total pressure. Okay, so that is just simply the partial pressure of H2, this is a formula by the way, is equal to the mole fraction of H2 times the total pressure. And if we're trying to find the total pressure like this question asks, in the concept, you can just simply have the total pressure to be the partial pressure of H2 divided by the mole fraction of H2. By the way, this can be done for all the components. So I'm doing this for H2, I can also do this for N2, but just for the purpose of this class online, we're just going to do one for H2, and in your own personal time, you can do the one for N2. So the total pressure would end up being P total would be the partial pressure of H2, which we solved here to be 2.0 atm atmosphere. So 2.0 atmosphere divided by the mole fraction of H2. We'll go back to the top And we see the mole fraction for H2 right here to the left is 0.667. So divided by 0.667. I don't know what's, yeah, 0.667. So if you look at this in your calculator, I apologize for the scribble. It's my pen being not serious. So 2.0 divided by 0.667 is going to give you 2.999 atmosphere, which of course when we do it to two sig figs, we're going to end up with 3.0 atmosphere. And that is how you solve it. And if you look at 3.0 atmosphere and you also look at what we solved when we added up the two partial pressures, you see that we get the answer. So one is just the commonsensical way, adding up the partial pressures you've solved individually, and one is the concept based way, which is the one I just taught you, which is applying the formula that the partial pressure of a component or of a gas is equal to the mole fraction times the total pressure. From that, you can determine what the total pressure is when you have the partial pressure and the mole fraction of a particular component. Hopefully, this is helpful. Make sure you try this method with the N2 gas, and you're going to see that you're also going to get to 3.0 atmosphere in two significant figures. I wish you guys all the very best. Salam and welcome everyone to my channel. So today we're going to be working on the perfect gas equation question or perfect gas question on the screen that says a vessel of volume 22.4 dm cubed, which is the same thing as volume 22.4 dm cubed, the same thing as 22.4 liters, contains 1.5 mole of H2 gas. So the number of moles of H2 gas is 1.5 mole and 2.5 mole of N2 gas. So the number of moles of N2 gas is 2.5 mole at 273.15 Kelvin. So temperature is 273.15 Kelvin. Calculate the mole fractions of each component, and 2, their partial pressures, and 3, their total pressure. So the mole fraction of each one of the components. So we're going to have to calculate the mole fraction of H2 gas as well as the mole fraction of N2 gas. And that is the first question. So the first thing you have to know is for us to know that the mole fraction of a particular component is simply the number of moles of that particular component. So number of moles of H2 divided by the total number of moles contained in the vessel or contained in the container or in the mixture. So we know we have two components, which is H2 gas as well as N2 gas. We've been given the number of moles for H2 gas and number of mole of N2 gas. So we know that the total number would just be the addition of both of them, which would be 1.5 mole plus 2.5 mole. That is that. That's how you do for that one, which is just simply the number of moles of H2 gas plus number of moles of N2. And then what is at the top of it is the number of moles of H2 gas, which is 1.5 mole. So that is how you handle this particular question. So that will be 1.5 mole divided by 4.0 mole. So you cancel out the mole and you just have 1.5 divided by 4.0, and whatever you have to be the answer is whatever is correct. So that will be xH2 equals to, or not xH2, the mole fraction of H2 gas is 1.5 divided by 4. So this is 0.375. Now we're going to do the exact same thing we did here, but for N2. And there are two ways of solving this. So I'm going to show you I'm just going to replicate what we've done above, and I'm going to show you like a shorthand method that you can use based on a particular concept. So the first method that we can use to find the second one will be number of moles of N2 is just the number of moles of, the mole fraction of N2 is simply the number of moles of N2 divided by the total number of moles. So the number of moles of N2 will simply be 2.5 mole divided by the total number of moles, which is 4.0 mole. So we're going to cancel out this and we're going to end up with 2.5 divided by 4.0, which is 0.625. So the mole fraction of this is just going to be of N2 gas is 0.625. So that's how you solve for this one. Now there is like a better method that you can use that is quicker. It's just understanding the simple math concept that fractions add up to a whole number. So in this particular case, since we're doing a fraction of something, we know it's going to add up to 1. So meaning that the mole fraction, in this case of H2 gas, and the mole fraction of N2 gas is going to give you 1, because of a fraction of 1 is just the mole fraction, sorry, it's just the mole divided by the total, and the fraction of the other is just that one's mole divided by the total. And all of this information will have to add up to 1, since we're dealing with fractions or decimals, whatever you want to call it. Fractions, they all add up to 1, because they are kind of into one another and a total that we've calculated to before. So this is just going to be us determining the mole fraction of N2 gas. We just have simply been 1 minus the mole fraction of H2 gas that we had solved earlier. So that would just have been simply 1 minus 0.375, and the mole fraction of N2 would have simply been 0.625. So that's how you solve it. This is like a quicker way to solve it based on the simple mathematical concept of learning about fractions. So we're done with the first part of the question. We have two more parts to work on. The second one is to determine the partial pressures of each one of the information. So the partial pressures would be PV equals to nRT. We have to use this because we're dealing with a perfect gas. So that would be PV equals to nRT is just the perfect gas formula, no perfect gas equation. So to find the partial pressure, we'll be focusing on one component at a time. So let's start with the one for H2. So that would be P H2V equals N H2 RT. Now, the number of moles we can clearly see is different in the question, and the number of moles of one is different from the other. It's important for you to know that when there are multiple components gases in a mixture or in a container or in a vessel, as in this case, you have to understand that the number of moles would be different, as well as the pressure that will be exerted will be different, because since the number of moles will be different, the pressure has to be different. But you see the temperature, the gas constant, and the volume, they don't change. They're independent of the number of gases in a vessel, but the pressure of one gas, or the pressure that one gas will exert, will be very different from the pressure another gas will exert, even though they are in the same container, because they have different number of moles, they have different masses. So different ways they can apply pressure to the walls of a container or to the walls of the vessel, but the volume of the vessel is independent of the two of them. The volume is just what the volume is. The temperature is just what the temperature is. Just like when you boil water, they just tell you the temperature of water. They don't tell you the temperature of hydrogen molecules in water, or the temperature of oxygen atom in the water. They don't do that. They just tell you the temperature of water. That's why we know that the temperature of the mixture is just temperature of mixture. You don't have the temperature of H2 gas, and you don't have the temperature of N2 gas separate. So the only thing that is gonna be different in this perfect gas formula for each one of the two different components will be the pressure and the number of moles. So now the partial pressure for H2 is simply going to be nRT, okay, or for H2 divided by V. So the number of moles of H2 is simply 1.5 mole times 0.08206 liters 8 atmosphere divided by mole Kelvin. Okay, all of that times temperature, which is 273.15 Kelvin, divided by volume, which is just simply 22.4 liters. So if you're confused, we can cross check. We can see 22.4 liters, 1.5 mole, 23.15 Kelvin. So we're going to cancel out the mole, because we're dealing with pressure. We only want the atmosphere unit to be there. So we have to cancel out mole, Kelvin, liters, and then we input our information in our calculator to get let's first of all rewrite this for anyone who's confused. So 1.5 times 0.08206 times 273.15, all of that information divided by 22.4, and then you have the atmospheres here, which is the unit for pressure. You put all of this information in a calculator to get 1.501 atmosphere. And if we want to stick to the two sig figs of our parameters, we end up with the pressure for H2 to be 1.5 atmospheres. So that is the answer to this particular part of the question. Now the second part, which is the pressure of N2 gas, which is NN2 times R times T divided by V, which is 2.5 mole times R, which is 0.08206 liters atmosphere divided by mole Kelvin, times temperature, which is 273.15 Kelvin, divided by the volume, which is 22.4 liters. So you cancel out all of the information and you cancel out the mole, the Kelvin, the liters, and you end up with P of N2 equals 2.5 times 0.08206 times 273.15 divided by 22.4. And then there's atmospheres here. You put all of this information into your calculator to get 2.502 atmospheres, and sticking to two sig figs, we end up getting the pressure of nitrogen into gas to be 2.5 atmospheres. So that is the second part of the question practically solved. Now, the third part of the question says we should determine their total pressure. So total pressure is simply you adding up the individual pressure. So the total pressure is just simply going to be the pressure of the N2 gas plus the pressure of the H2 gas, and that is it. So we have the pressure of the N2 gas here, which is 2.5 atmosphere, and we have the pressure of the H2 gas, which is 1.5 atmosphere. When you add both of them up, you end up with 4.0 atmosphere, and the total pressure is 4.0 atmosphere. And that is how to answer this question. Now, this is all done, but I want to teach you another way to find the total pressure, which is like quicker, especially when if you're asked this question in a multiple choice way, right? Meaning if you're asked the question and time is important, or in a multiple choice question and you cannot you can't be solving all of this information. Now, look at this like big black box that I'm doing here. Concept based to solve the total pressure. It's important for you to know using the mole fraction and partial fraction. So let's say the mole fraction of H2 gas, right? Where we know that, and we have the partial pressure of H2 gas. Say you're given a question where you're now, just from these two information, you're supposed to find the total pressure, right? So basically, we already know they're already giving us the mole fraction of H2 gas. We've solved for it, which is 0.375. And we already have the partial pressure for hydrogen gas to be 1.5 atmospheres, okay? So from this information, we are supposed to find the total pressure. So now, note that this is how basically the general formula for this particular concept is. The partial pressure of H2 gas, okay, is going to be equal to the mole fraction of H2 gas times the total pressure. So if you're ever given a question, multiple choice based question, where you're given all of this information, but you need to solve your work fast and you don't have the time to be calculating the one for the N2 and all of that, this is a perfect equation to use, right? This is very, very important. So to find the total pressure in this particular case, we just have P total equals P H2, the partial pressure of H2 divided by the mole fraction of H2. That is how you solve this. So partial pressure of H2, we know that to be 1.5 atmosphere divided by the mole fraction of H2. We know that when we look at this, we know that to be 0.375. When we put it in our calculator, 1.5 divided by 0.375, we get P total to be 4.0 atmospheres. I would advise everyone to try this on their calculator. You're going to see it's very true. The funny thing about this particular one is that you can also repeat this concept to just N2 gas. You can instead of having H2 here, you can instead substitute the N2 information. So the partial pressure of N2 gas, right, equals the mole fraction of N2 gas times the P total. And you can go on to find the pressure of N2 gas, the partial pressure of N2 gas divided by the mole fraction of N2 gas. And you're going to see that you're also going to get 4.0. This is a quicker way of doing this rather than like calculating for each one of them to find the total. But because this question is asking you for each individual information, we have to put everything out in order for us to like do it right. So yeah, that's how you solve this. Thank you for staying with me. If you have any questions for physical chemistry, make sure you put it in the comment section. Salam and hello, everyone. We are asked this question. A gas mixture consists of 320 milligrams of methane, 175 milligrams of argon, and 225 milligrams of neon. So we're going to break this down because that's the first thing you do anytime you're given a question in physical chemistry or thermodynamics. It's best for you to like put down all the parameters you're given step by step. So we're told 320 milligrams of methane, which is the same thing as CH4. Well, because usually we deal with grams in chemistry, we're going to convert this from milligrams to grams. It's important for you to know that milligrams is the same thing as times 10 raised to the power negative 3 grams. So this means we're going to push the decimal point 320.0, this one, 3 times to the left in order for us to convert from milligrams to grams. So this 320 milligrams is the same thing as saying 0.320 grams of CH4. Okay. Now we also have the next one, which is 0.175 grams of argon, which is the same thing as 175 milligrams, and then 0.225 grams of neon. So having this information down is critical. The next thing we have to understand is that we are told the pressure of neon, which is pressure of neon is 8.87 kilo Pascal, right? That's the thing that you've told us. It's important for you to know that this particular question is dealing with Dalton's law of partial pressures, where the total pressure of a mixture is equivalent to the pressure of is equivalent to the total of the pressure of each individual gas in the mixture, right? So you have 8.87 kilopascal. Now we only know the pressure of neon because this is a gas mixture. So anytime that you're dealing with a gas mixture, and you have different gas components in the mixture, you have to understand that the pressure that each one of the gases will exert would be different, right? Except if the question tells you otherwise, that it's the same exact pressure. So the total pressure is not going to be just the pressure of one gas, it's going to be the pressure of every single gas. So this is 8.87 kilopascal. So this is just the pressure of neon. But then they mentioned the pressure of neon at 300K. Well, 300K is us them telling us that the temperature of the mixture is 300 kelvins. Now, I wanted to mention that I'm sorry, this temperature is not the temperature for just neon. This is the temperature of the entire mixture, meaning the temperature of 300K is going to affect both methane, argon, and neon, not just neon. They just kind of wrote the question in a way that makes it look like the temperature for neon is going to be different for the temperature for methane and argon. No, it's like you boiling water and they tell you the temperature of water is this. Water is consists of H2O. Yeah, and they're not going to tell you the temperature of one hydrogen or one of the two hydrogen atoms in the water molecule is 300K, and then the oxygen is 600K. The entire temperature of the mixture is, for example, 300K. I'm only using this to denote, just to tell you that the temperature of the mixture is going to be the same regardless of the number of different gas components in the mixture. So this temperature is the temperature for every single component in this gas mixture. So we have the temperature now, we have the pressure for neon, we have the mass of everything. Now we're asked to determine the volume as well as the total pressure, which is P tot of the mixture. That's what this question is asking us to do. Now, the first thing you have to do is anytime you're asked to find the volume, we will go back to our understanding of the perfect gas formula, which is PV equals to nRT. We've been given the temperature, so that is good. We know what the gas constant is going to be because it's a constant. We know the pressure of just one component. Now we're going to be wondering, how do we solve this? Well, it's important for you to know that whenever you're dealing with whenever you're dealing with mixtures with multiple gases, the number of mole that one gas component exerts is different from the number of mole that the other in the mixture exerts. Now we have three different ones. We have methane, argon, and neon. It has to tell you that the number of moles of methane, right, N of CH4 is going to be different from the number of moles of argon in the mixture, right? And the number of moles of neon would be different. So it's not only the pressure that is affected, the number of moles is also going to be affected. Meaning the volume, the gas constant, the temperature are the only things that would be consistent regardless of the mixture. They're going to be the same. So when we calculate the volume is not going to be separate for each one of the different components. It's just going to be one volume, one temperature, one gas constant. But pressure that will be exerted because of the number of the mass of the gas is different. The pressure would be different, and also the number of moles would be different. So we've been given just the number of moles. We've been given just the pressure of um what's it called, the pressure of neon. So we're gonna have to use the number of moles of neon to solve this. So this is gonna be the pressure of neon is gonna what we will use times the volume equals the number of moles of neon times R times T. So to find the volume, we end up writing this in terms of volume. So we have the number of moles of neon times R times T divided by the pressure of neon. So this is going to be number of moles of neon. We already know that 0.225 grams of neon. So in chemistry, basic chemistry, we know that number of moles is always going to equal of a gas or of anything, of an element, an atom, all of that. Number of moles is always going to be the mass over the molar mass. We have the mass of neon to be 0.225 grams, and we have the molar mass of neon to be, even though we don't have this information on the screen, you can just Google it, which is what I'm going to do, or you can use your periodic table. So the molar mass of neon is 20.18 gram per mole. So we insert this in a calculator, we cancel out the grams, and we would insert this information in a calculator to get B 0.11150 mole. So we've determined the number of moles of neon. Now we can input this information into the calculation. So that's going to be volume equals number of moles of neon will be 0.11150 mole times R. The R that we need, the gas constant we need, is going to be determined by whatever the units are. So we have mole unit, we have Kelvin unit, and we have the volume. We've not determined the volume, but we have our pressure in kilopascal. So what we're going to be using is the gas constant 8.3145. Okay, kilopascal liter divided by mole Kelvin. So that is what we're going to be using. This is gas constant because we also have the gas constant 0.08206. That one works whenever we're doing liters, atmosphere divided by mole Kelvin. In this case, we're dealing with kilopascal, so the gas constant is going to be different. So we only have two gas constants, and that's determined by the units that we're given in the question. So in this case, we're going to use 8.3145. Okay, 8.3145 kilopascal times liters divided by mole Kelvin. And then lastly, times, we've got number of moles R, and we've got temperature, which is 300 Kelvin. All of that information divided by pressure, which is 8.87 kilopascal. So we're going to cancel this out. We're going to cancel out the moles. We're going to cancel out the Kelvin units. We're going to cancel out the kilopascal. And what we're going to end up with is just information involving volume. So volume is going to be all of this information inputted in a calculator. So we have 0.1150 times 8. Please do it with in your calculator as well. 8.3145 times 300 Kelvin divided by 8.87 kilopascal. So that's going to be 3.13542 liters, which you would do the sig figs, since we've been given everything in three sig figs. So the volume is going to be 3.14 liters. So we've been able to do half the question. Now we're going to go to the total pressure of the mixture. Well, if you remember, I told you Dalton's law of partial pressures. We're going to have to determine the pressure of methane, okay, as well as the pressure for argon in order for us to be able to determine the total pressure. So when we determine the pressure for methane, the pressure for argon, and we've been given the pressure of neon, we can add them up to determine the total pressure. So the next thing we're going to do is let's determine the pressure for methane. So the pressure for CH4 is going to simply be what we know is going to be this times the volume using the perfect gas law equals the number of moles for the methane gas times R times T. So determining the pressure would just be P, the pressure of methane equals the number of moles of CH4. We're just doing everything in terms of pressure of methane times R times T divided by volume. We've determined what the volume is. So we have the pressure of CH4 to be number of moles of CH4. We're going to do the exact same thing, right? We know we have to determine the mass. That's going to be the mass of CH4 divided by the molar mass of CH4. Okay, times R times T, all of that information divided by the volume. So that's what you're going to do here. And when we do that, we will end up with, let me draw something that separates it. So the pressure of CH4. Make this a little bit smaller and we can focus on this part of the work. So we have the mass of CH4. We've determined it over here. Oh no, we've been given it over here to be 0.320 grams. So that would be 0.320 grams divided by the molar mass of methane. You can Google what that is online. So molar mass of CH4, which is methane, that would be 16.04 gram per mole divided by 16.04 gram per mole. Okay, times R, which is simply 8.3145 kilopascal times liters divided by mole Kelvin times the temperature, which is 300 Kelvin. All of that information divided by volume. Let us use the volume without the three sig figs in order for us to maximize the calculation. So we have 3.13542. It's not good for you to use the estimated value of things to do further solution. You can only give the estimate of something after you've done all the calculation, if that makes any sense. So we've got grams. We're going to cancel our grams. We're going to cancel out the liters. We're going to cancel out the Kelvin. And we're going to cancel out the mole, because we're trying to find pressure. So all our answer has to be in kilopascal. So when you do this pressure here, we're going to the pressure of CH4, we're going to now go on to write E 15.871 kilopascal, which is the three sig figs of this is going to simply be put here. So the pressure of methane gas is going to be 15.9 kilopascal. So we've gotten the pressure of methane gas. The next thing we're going to do is to determine the pressure of the third one, which is argon. So we're just going to take this up a little bit. So the pressure of argon would be equals the number of moles of argon times R times T divided by the volume. So the pressure of argon would be, for us to do this, the number of moles, the mass of argon that we're given. Just basically what we did for CH4 methane, we're going to do it here, times divided by the molar mass of argon that we're given. So just a repetition of what was above, times R times T divided by the volume. Number of the mass of argon, we have that to be 0.175. I'm sorry, 0.175 of argon. So that would be 0.175 grams divided by the molar mass of argon. That's 39.948 gram per mole times the gas constant 8.3145 kilopascal times liters divided by mole Kelvin times 300 K divided by volume, which is 3.1354 liters. So you cancel that out. So you cancel grams, you cancel grams, you cancel mole, you cancel mole, cancel Kelvin, you cancel Kelvin, you cancel liters, you cancel liters. So what you end up with is, so you input all of this information to the calculator, and that's what I'm trying to do. So what you end up with is 3.4850 kilopascal. So that is what you get as the pressure of argon. So now the total pressure of this is going to be the pressure of argon plus the pressure of methane, CH4, plus the pressure of our beloved neon. Is when we add all of this up, we're going to get the total pressure. So this would be, total pressure would be 3.4850 kilopascal plus the pressure of CH4 15.9, sorry, 15.871 kilopascal, because it's wise for you to always use the unapproximated or unestimated version, not before doing your calculations. You can only use like you can only use that to find the proper estimate, so you don't end up making mistake in your work. So plus 15 point, sorry, plus 15.871 kilopascal plus the pressure of neon, which was given to us in our question to be 8.87 kilopascal. So we put that down because that's what we're given, 8.87 kilopascal. Then you add all of this information up to get 28.226 kilopascal, which we would do the sig figs for to be 28.2 kilopascal at three significant figures, because that's where all our questions, how our questions has been given. So the total pressure is 28.2 kilopascal. So please look at your work and look at everything we've done. We've been able to successfully determine the volume at the beginning, which is 3.14 liters, and we've done the work to get it. We first of all went to use our we first of all determined the volume by using the pressure that we were given and the number of moles that we were given, or the number of what the mass that we were given. We used to determine the number of moles, and we put that into the gas equation, and we determined the volume of the entire mixture because we used the pressure of neon that we're given. Then when we determined the volume, we used the volume to determine each one of the pressure in the mixture. We determined the methane gas pressure, and we also went on to determine the argon mixture. When we had all three of this information, we're able to add each one of the individual pressure to get the total pressure. This question is a perfect application of Dalton's law of partial pressure. Hopefully, I've been able to successfully teach you guys. I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.